Hi there once again. Alright, so now in this video we're going to look at another type of stationary point. We looked at two types of stationary points. One is a minimum and the other a maximum. The point of inflection is the third type of stationary point. The point of inflection. Okay, point of inflection, not infection, inflection. Alright, now you get this with cubic graphs. Okay, remember I told you there are two types of cubic graphs. Well, the ones that have a wiggle in the middle and the other that do this. Okay, so this is actually the, if I drew, let me use another color. If I drew some axes x and y for this graph, that's actually the y is equal to x cube graph. Y is equal to x cube. Alright, now let's work out where the stationary point is for this graph. Okay, now we definitely know the stationary point is here, okay, on the origin. Okay, so that's a flat line there on the origin. Alright, so if I differentiated this, so if I were to differentiate this, dy by dx is equal to 3x squared. Alright, and I know at my stationary point the gradient is 0, so 0 is equal to 3x squared. So therefore if I were to figure out what x is, x squared would be equal to 0. So x has only one result, x is equal to only 0. Okay, so even though it is a cubic equation, it has only one stationary point. Okay, so you've learned about the maximum, the minimum. Now this one doesn't look like a maximum nor a minimum. Okay, so this is called a point of inflection. But how would you prove that this is a point of inflection using the second derivative? So if I were to work out the second derivative of this, which would be d squared y over dx squared, which would be 6x. Okay, so the second derivative equation, I substitute x is equal to 0, I get my second derivative giving me a value of 0. Now 0 is neither positive nor negative. Alright, so that's an important point there. When you get a value of 0 for your second derivative, it's a point of inflection, and that's how you identify a stationary point that is a point of inflection. Okay, let's figure out the stationary point for another cubic graph where you'd expect to see a point of inflection. Okay, just have a look at this equation. So that's your equation. So if I differentiate this, I get, that's my first differential, and to find my stationary point I make my gradient 0. Alright, and I figure out the values of x that satisfy this equation. Okay, now even though we had a quadratic for our first differential, we don't have two values of x as our results. We just have one value of x as our result. X is equal to 1. Okay, so that gives us an indication now that the graph actually looks like this and not like this. Okay, because only a cubic graph that looks like this could have one stationary point. Whereas a cubic graph that has two stationary points, you would expect it to look like this. Okay, so let's work out the second differential, and if I substitute x is equal to 1 into this, I would get a value of 0 for my second differential. So therefore that's indeed a point of inflection. Okay, because my second differential yielded a value of 0. Okay, so let me summarize what we've learned so far. Alright, so if my second differential, that's d squared y dx squared, gives me a value that is greater than 0, meaning it's a positive value, okay, meaning it's positive, then that's a minimum. Okay, if my second differential was negative, meaning it was less than 0, that means my stationary point, its maximum, if my second differential is equal to 0, then it's a point of inflection. Okay, alright, so let me draw some graphs to show you what they are. So that's a minimum, oops, sorry, that's not what I meant to draw. Minimum, so that, no, that's this way, and maximum is this way. A point of inflection would look something like this. So let me put dots at these points. So that's a minimum, that's a maximum, that's a point of inflection, and at all these points the gradient is equal to 0. Okay, let's move on to something new now. You get asked this in exams. You're asked to use you're asked to figure out which part of the function is increasing or which part of the function is decreasing. Okay, now for straight line graphs, it could be either increasing or decreasing. Okay, so a graph like this, let's call that y is equal to 2x plus 3. That's definitely an increasing function, because as you go along, as you go along the values of x, the y values keep on increasing. Okay, so at x is equal to 1, you'd expect it to be 5. At x is equal to 2, you'd expect it to be 7. So the y values progressively increase. A function like this, so that's y is equal to 3 minus 2x, the values decrease as you move along the x values. Okay, so at x is equal to 0, the value of y is 3. At x is equal to 1, the value of y is 1. So the values are decreasing. Okay, whereas for a parabola, it's slightly different. You have parts of the parabola where it's increasing, you have parts of the parabola where it's decreasing. Alright, let me draw a dotted line up to the point where you have the minimum point for this parabola. Okay, from here to here, you find that the parabola is decreasing, because if you looked at the gradient along this parabola, the gradient is negative. Okay, the gradient or the tangent, if you drew a tangent at any point here, would slope this way. Okay, let me just draw you a tangent. Let me use a finer pencil for this. So the tangent there would be more or less vertical, a big slope there, and a small slope here. Now all of these slopes, these tangents, are have a slope similar to this. So if you worked out the equations for these, they'd definitely be negative. Okay, so anywhere beyond this point, where the stationary point is at, you'd say that the function is decreasing anywhere beyond this. Okay, so let's say our stationary point was -1, so x is smaller than -1, the values are decreasing. Okay, I don't need to say smaller than or equal to, because if my stationary point is at -1, let's just say this is the coordinate, at 0 it's neither decreasing or increasing, because it's just a flat line. Okay, so I have to say the values of x where it's decreasing is less than 1. Okay, so now you'd know what I'd do next. The values for which this graph is increasing is the points beyond the stationary point. So any point beyond the stationary point going this way, it's increasing. So that's increasing, that's decreasing. Okay, so the inequality showing the decreasing values, so that's the inequality showing the decreasing values. The inequality showing the increasing values would be what? It would be x is greater than -1. Okay, so that way you'd work out which parts of the function is the function increasing and which part of the function is the function decreasing. Okay, right, so let's look at a parabola which looks like this, and I'll say that's the stationary point, and the coordinates for that would be, I'll just say that's 2, 5. Alright, so now for this one, which values of x is increasing for this function and which values of x is decreasing for this function. So I'll give you a minute and we'll look at the answers in a minute. Okay, so here are the answers. Alright, so any point beyond this x value going this way, it's a increasing function because the slopes are positive. Alright, so when x is smaller than 2 it's increasing, but when x is greater than 2 it's decreasing. Alright, good. Okay, now we'll look at a cubic graph and see which parts of the graph is increasing and which parts of the graph is decreasing. Okay, so let's do this for a cubic graph. The equation is this. I will have to first sketch this equation. Alright, so I'll need to know the stationary points, so that will give me a clue as to how this cubic graph will look like. Okay, so I differentiate to figure out the stationary points, dy by dx, and I make dy by dx equal to 0. Okay, so these two are my stationary points, and I know that my graph looks like this because the x cubed term is positive. If the x cubed term was negative, it'll be the other way around. It'll go down like this, come up, and then go down like this again. Alright, because my x cubed term is positive, it'll look like this. So the first stationary point is definitely a negative third here, and the other stationary point is 1. Alright. Alright, now for this graph, which values of x is this function increasing? Okay, notice all the slopes, the gradients, that would give you a positive value. Like if you drew a straight line, it will give you a positive gradient. Okay, now these slopes here would be positive. Okay, the blue ones, the light blue ones. Okay, so what values are those? Okay, it would be x, one moment please, x is greater, or x is less than a third, a negative third. X is less than a negative third, and x is greater than 1. So for these values here, it's increasing. Now then, for which values of x is this function decreasing? Notice the green ones, the green lines. Okay, now these green lines, if you drew straight line equations, those straight line equations would have a negative gradient there. Okay, so the green lines are the ones indicating the decreasing function. So that would be x is between, so x is greater than a negative third and x is less than 1 for the decreasing function values. Okay, alright, so let me go through this again, how you would arrive at this result. You first get the equation and then you differentiate it, and then you figure out where your stationary points are. Okay, and then you draw a rough sketch of the graph, and then you notice how the gradients look. Okay, another way of doing this, if you don't know how to sketch this graph, is to work out individual points. Now this is quite tedious, so you would have to work out the gradient of a point that is to the left of this negative third. So a point that is to the left of this would be something like negative 2, or I'll just say negative 1. That's easy. Negative 1, and I substitute this into this equation. If I substitute negative 1 into this, I should get, that's negative 1 squared, 2 times negative 1, that's plus 2 because of the minuses. So that's 3 plus 2, 5, that's 4. Okay, the gradient is 4. Okay, if I substitute negative 1 into this, the gradient is 4. So therefore that's increasing. Okay, alright. Whereas if I substitute a point to the right of this, let's say x is equal to 0, I would get minus 1, okay, as my gradient. Okay, so my white ink is actually the coordinate itself. Alright, the red ink tells me what the gradient value at that point is. Okay, so at minus 1 the gradient was 4, positive 4, so it's increasing. At coordinate 0 my gradient is negative 1, so it's decreasing. Okay, and then you check 2 points to the left and to the right of this stationary point. So we already have a point to its left, which is 0, so we'll look at a point to its right. So let's look at x is equal to 2. Alright, If I substitute that into that, I get 4. That's